All right, so we need to start out with going over the equilibrium homework. I did load the answer key this afternoon, so you can go back and look at it prior to the test. I haven't turned on the test for scheduling purposes yet. It should go live Thursday night so that you have Friday, Saturday, Sunday, and Monday in order to figure out when you want to take the test during that window. All right, let me try to do the share screen thing here. All right, let's go through the equilibrium homework. So the first one has two reactants that are separate and two products to the same thing. And I gave you partial pressures for all three of your items. So first thing you need to do is write your equilibrium expression, paying attention to the fact that the NO value needs to be squared because it has a coefficient of 2 out in front. Then plug in all your numbers. So we've got 0.05 squared on the top, we've got 0.15 and 0.33 on the bottom. Crunch all your numbers, and you end up with a Kp value of 0.015. It is a Kp specifically because the values are given in terms of atmospheres as opposed to being given in terms of molarity. Next one. This one is not mathy. It's just trying to make sure that you are setting up the equilibrium expression correctly. Since you have 3 hydrogens, that means your hydrogen value needs to be cubed. You have a single nitrogen molecule, but you have 2 NH3s, so that value needs to be squared. So make sure that you have products on the top, reactants on the bottom. Then we get into the number crunching and the ICE table idea. So this one has a Kc. Now note that your moles of your reactants there, the hydrogen and the nitrogen, it tells you how many moles you have, but they're placed in a 1 liter container. So this is an indirect way of telling you that you have a molarity as your concentration. So I set it up in the order in which they are presented in the equation. So we've got nitrogen, then hydrogen, then N2H4. Remember, I is for initial. So we have 1 molar and 2 molar for my nitrogen and my hydrogen. And your original, your starting point implies that you have no product, so no N2H4 at all to start with. It is going to flow toward the empty spot. So it is going to flow in the direction of your N2H4. This means that you're going to subtract X from your nitrogen. You're going to have to subtract 2X from your hydrogen and add 1X to your N2H4. So then at equilibrium, this is going to give you the 1 minus X, the 2 minus 2X, and the X alone for the N2H4. Now, once you set this up, you end up with a situation where if you did not remember that because the 2 coefficient in front of your hydrogen means that you need to square the values, and you look at the bottom part of your setup there, I've got a 1 minus X in my parens, and then a 2 minus 2X squared, which means if you attempted to do this all the way out such that you did the full-on algebraic solving method, the problem is you end up with a cubed value for X, which we did not create a method for solving for that. You need to use the approximation method in order to make this work, because otherwise it becomes unsolvable. I am going to make the assumption that my X value is a great deal smaller than my original concentrations of 1 and 2 molar, such that it then becomes 1 and 2 squared, and the X's on the bottom go away. Now, granted, the X has to stay on the top because you actually have to solve for something, but the ones on the bottom end up dropping out. Once I finish the math for that, that will give me an X value of 0.02. So that means my nitrogen is the 1 molar minus 0.02, so 0.98. You have to have 2 minus 2 times the X value for the hydrogen. This should give you 1.96. And the last part there, since you have a single X value for your N2H4, it is the value that you solved for, which is 0.02. If you made mistakes in your homework, chances are the most likely mistakes for that problem were not realizing that if you didn't use the approximation method, that this gave you a cubed. Some people didn't include the squared part. And so it was less obvious and also unfortunately wrong too, in terms of how you solve for your X there. All right, moving onward to one that is presented a little bit differently. We've got COCl2, so one reactant. This is a decomposition reaction. And it gives you CO and Cl2 as your products. Now, I gave you a Kc, but I gave you initial pressure in atmospheres. This means that you must convert from Kc to Kp. So this was a little bit of a synthesis style problem in that you needed to pull two pieces of information together in order to make this work. First, you had to do your conversion. So if you look there on kind of the left-hand side there, I've got Kc and 0.0821 T delta N. So in this case, I actually also realized I forgot to put my number in after the equal sign. Oh, that was really dumb. Let me go back and fix this so you can see where I put this in. I forgot that 4.63 times 10 to the negative third is actually supposed to go there where the Kc value is. Otherwise, you're missing a piece of information. All right. This then gives you ultimately a Kp value of 0.304. Remember that if your number of reactant molecules and your number of product molecules don't match, in this case I have 2 and 1, then your Kc and your Kp will not be identical numbers. Once you figure that out, of course, now this sort of scrunched up my line up here a little bit. There, that looks a little bit better. I've got an initial of 0.76. I have no products to start with. So again, this is one of those things where it needs to flow toward the right, toward the product side. So this is going to give me a minus X on my COCl2 and a plus X and a plus X on my CO and Cl2. Come all the way down to your equilibrium line. You have 0.760 minus X and X and X. Now this one, because you barely have 100-fold difference, 0.76 versus 0.340. Actually, it's not even a 100-fold difference. Actually, I was looking at the KC. You have the same order of magnitude. Okay, they're both, if you wrote them in some scientific notation, they're both 10 to the minus 1. So you can't use the approximation method. You've got to crunch your way through the quadratic. Otherwise, you're going to end up with really skewed values. So I algebraically rearranged it. And that gives me x squared, 0.304x, and minus 0.231. So my A, my B, and my C. A of 1, B of 0.304, C value of 0.231. Crunch it through the quadratic. And remember, the reason my square root sign looks a little bit weird there is this is a problem peculiar to Microsoft Word in that it gives me the front end. I don't know if you can kind of see here. It's like this bit right there. Okay, that's the front end of my square root sign that it doesn't show you the top of. So it looks kind of weird when you're examining it. Crunch all your numbers. You end up with 2 roots because that's the way quadratic formulas work. You end up with 2 roots. And per relatively usual, one of those roots is negative. You can't have negative molarity, so that automatically ditches out that one. That will give me 0.352 as my x value. So this will give you CO and Cl2 having a pressure of 0.352 atmospheres. And your CoCl2, once you subtract, ends up with a pressure of 0.408. Now, the next one does have identical Kp versus Kc, because you have 2 molecules on the left-hand side, your H2 and your Cl2, and you have 2 molecules on the right-hand side, 2 HCl's. So this gives you Kp equal to Kc. So I set up my numbers here. I'm going to have 0.47. I have no chlorine. I have 3.59 of my hydrochloric. Now, since it has to flow toward the empty spot, what this means is in order to have at least a little bit of the Cl2, that also means that my H2 is going to increase because it is flowing to the left. And when I get to the E part of my ice chart there, I've got 0.47 plus X, excuse me, just X alone for my Cl2, and 3.59 minus 2X for my hydrochloric. This is another messy one in that when you look at your values, chances are you probably can't round on this one either because it exceeds the 5% rule. If I start crunching my numbers here, I've got the 2x squared on the top. So 3.59 minus 2x squared. Remember, FOIL, first, outer, inner, last. And the bottom, I have 0.47 plus x, and then I have another x. So by the time I crunch all of that, and actually I didn't realize why it turned my line here in my quadratic formula. The stripe is black, I don't know why, but that doesn't actually affect the math. Crunch, crunch, crunch. Quadratic formula, a messy quadratic formula, gives you 2 roots of 0.1 and negative 0.65. So obviously can't use the negative one. This also is not the end of the problem either. Okay, this tells us how many moles are at equilibrium. We've got 0.57, 0.1, and 3.39. That gives you a total of 4.06 moles. So here comes the last piece of this puzzle. Because we're talking about partial pressures and the fact that we want the entire pressure of our container to be 2 atmospheres, I need to do it as mole fractions. So each one of my molecules, H2Cl2, HCl, have the number of moles that you just solved for on the top. They have the 4.06 total on the bottom. Then multiply by 2 atmospheres, and this will give you 0.28, 0.049. If you rounded it and called it 0.05, that was fine, and 0.167. So those are my pressures once I reached equilibrium. Then we hit Le Chatelier's, the idea of, does it go left, does it go right, or does it not really change at all? So look at your reaction. We've got NO and SO3. We've got NO2 and SO2 as products. So if I have less NO, it is going to shift to the left in order to try to regenerate the part that you took away. If you have more SO3, it will shift right, trying to use up the additional that you dumped in there. If you have less NO2, that will also make it shift right as you try to create a little bit more to regenerate what you removed. And more NO2, okay, that's going to squish it back to the left. Increasing the volume in this particular case has no effect. Okay, why does it have no effect? It has no effect because you have the same number of molecules on the left that you have on the right. One of the things we commented when we talked about Le Chatelier's was, if you have differing numbers of molecules, like maybe one side is 3 and the other side is 2, then changing pressure and volume may cause a left or a right shift. But if they're equivalent, then you don't have an effect. The catalyst also has no effect because in terms of equilibrium, it may be going faster, but it's going faster in both directions at the same time. So no net effect might be a more descriptive way to say that. And then the final one, I gave you a number value for the K, 3.5 times 10 to the fourth. And therefore, because the number is greater than 10, you end up with more products favored. Questions about the homework set? Okay, let us talk about test stuff, since test is your next upcoming major event, beside the fact that I see some of you for lab tomorrow. So for the test, so 2 chapters, we have equilibrium and kinetics, 2 somewhat different topics. They are combined together. So think about things that you need to know for kinetics. You need to know things like how to find the rate law. Okay, this all sort of borders back into the homework sets. How to write your rate law. What exponent do you need? Remember that your exponents have a really limited number of possibilities. 0, 1, 2, 3. That's pretty much it as far as exponents that go into your rate law. We talked about how to use the data to find that, how to find a K. We talked about first order and second order, both from the write the rate law point of view, but also from the integrated version. We talked about half-lives, which are tied into the whole integrated idea also. And the last couple of things in that chapter had to do with molecularity and catalysts. Okay, so all of those are topics from the kinetics chapter. Then equilibrium, as we've just been going through on the homework, we've got, okay, can you write an equilibrium expression? Specifically, can you write it solving or write it out using the molarity notation, which is using the square brackets? Or are you writing it with the capital letter P's that are the way you denote pressures? Solve for equilibrium at whatever set of conditions are given. Use an ice chart. Can you round and approximate, or based upon the numbers that you get, are you just going to have to crunch the quadratic end of it? Can you convert back and forth between Kc and Kp? Le Chatelier's. Are you shifting left because of what you've changed? Are you shifting right because of what you changed? Or was there no net change at all? Also, the whole thing that was tied into the last question there of when you're looking at your K values, remember we said that there's two main brackets for that of, is it less than 0.1? Is it greater than 10? Or are you in that little gray area in between that is between 0.1 and 10, which chances are means you really are going to need the quadratic to make this work. There are 30 questions. They are a mix of multiple choice, couple of short answers, and problems. You'll get a 4-hour time limit for this, which should be significantly more than you need, but it's there if you need it. Like I said, I will set it so that it turns on basically at midnight on Thursday after class, and that will give you Friday, Saturday, Sunday, and Monday. It'll go off at midnight on Monday. So that gives you a 4-day window. So hopefully, depending upon work schedules and things like that, that will give you enough flexibility to pick a time that you can do the test in. Other questions regarding test information? I think I successfully got all of the videos downloaded, crunched through YouTube, and there might be one video. Actually, it occurred to me that I think I downloaded it to my hard drive, and I think I uploaded it to YouTube, but of course, because it takes a while for it to crunch through the system, I'm not sure if I published the link to the very last lecture we had right before we all went off to spring break. So I might actually have to put up one more link for that, but I've got most of the other ones caught up. So if you need to go back and watch something because you missed a piece of it, or you just want to go back and double check explanations, that kind of thing, they should be available. Questions? Otherwise, we are going to continue down the pathway toward acid-base equilibrium. Which means I have to figure out which folder I stuck it in. And it wasn't that one. these days I'm going to get everything all sorted out. Found the right file. All right. We got through a little of the auto ionization and a little bit of KW and how you decide if your solution is acidic or basic. I think that's about as far as I got. All right, so let's pick up with the second example here of looking at your hydroxide concentration. This one, I gave you a less pretty number instead of just 1 times something to an exponent. This one is 0.00037. But because your KW is an unchanging value, it's a constant. When I rearrange this and put my 1 to the negative 14th on the top and put the thing that I know, which is the 00037, crunch that pair of numbers, and you end up with a hydrogen concentration of 2.7 times 10 to the negative 11th. Now, here are some things to keep in mind. Because of the fact that your KW has an exponent of negative 14, for the purpose of acids and bases, you are not going to see a smaller exponent than negative 14. So you can't get negative 16s, negative 18s, negative 20s, that kind of thing. Basically, when you hit the bottom end there, you have 1 times 10 to the negative 14th, and that's pretty much as low as you can possibly go. On the other end of that scenario, you're not going to end up with something higher than something with a single decimal place, like say, for instance, 0.6. Okay, that would be 6 times 10 to the negative 1. So you have this limit. Okay, kind of like when we were talking about kinetics. Kinetics is only allowed to have certain numbers when we're talking about rate laws, 0, 1, 2, 3. There are some limits that are imposed on your acid base numbers here. So 10 to the negative 1 down to 10 to the negative 14, all the options in between, but not like you couldn't have 6 molar. Okay, not for calculating pHs and all that sort of thing. All right, which segues into pHs. Although I didn't quite finish the last line there on my hydroxide problem. So I knew that my hydroxide as given data was 0.00037. That's a bigger number than 2.7 times 10 to the negative 11th. So because my hydroxide concentration is bigger than my hydrogen ion concentration, this is what tells you that it is a basic solution. All right, now the segue. pH. P in math is a function. You can take P of basically anything. Okay, lowercase p. In this case, pH is negative log of hydrogen ion concentration. Make sure you are using log base 10 and not natural log. pH is something that gets tossed around when people talk about things like your soap, or the weird thing where they're selling smart water that is supposed to be pH balanced and some other things like that, which from a chemistry point of view is a really weird concept, because even if it was a little bit basic, too basic is going to hurt your gut lining the same way too acidic hurts the gut lining if you drank it as opposed to it already being produced by your stomach acid. So anyway, pH runs from 0 to 14. 0 is the bottom end. So although I will tell you that technically speaking, if you had really, really super concentrated something like hydrochloric or nitric, you can technically get a pH of -1, but we're going to kind of ignore that fact. 7 is dead in the middle. 7.0 is neutral. 14, that's the upper end. We've got really crazy basic. So some things to think about, and let me talk about this for a moment here. Actually, I'm going to pop up the whiteboard for a moment to give you a little information that I think is mirrored in your textbook. But all right. So pH, let's say 2 to 3. So nice everyday substances to kind of give you some reference points on how this sort of works. So lemon juice is pretty sour, okay? But part of its sourness lies in the fact that it has a really relatively low pH. If you have vinegar, okay, vinegar is usually pH around 5 or so. Okay, what's in the middle? Okay, there's not really much that's absolutely perfectly neutral. But there are some things that are close. For instance, milk. Actually, I should go pH, let's say about 7.2 to 7.5 is milk. Since we're talking organic substances that come out of mammals at this point, pH of roughly a similar thing is blood, okay? If your blood is much less than 7.1, you're heading toward ketoacidosis. If your blood pH is much above 7.4, you have some different problems that usually are or may be tied into things like hyperventilating, having too much carbon dioxide in your system tends to raise your blood pH a little bit. If we want to go up a little bit here, pH of about 8-ish. Spice, turmeric, stuff that makes curry yellow. And actually, I spelled that wrong. I think there's actually another R in there. I think it's turmeric. It is around pH 8 or so. And then we start getting to the upper end, pH 13, 14. We stop getting things you actually want to touch at all. Drain cleaner, okay, which is predominantly sodium hydroxide. If you had oven cleaner, Easy Off comes in a spray can. is mostly potassium hydroxide. I'm trying to think what else is in the basic range. Baking soda. Baking soda is probably pH 8 to 9. It's a little on the basic end, not super basic. Obviously, we cook with it. If you have an upset stomach, one really old school way to kind of minimize the acid in your stomach, way before Tagamet and Prilosec and all those sorts of things, a way to minimize acidity in the stomach is put a little baking soda in water, and yeah, it tastes kind of nasty when you drink it, but it neutralizes some of the acid because it's a mild base. So this gives you at least a little bit of a clue on some things that you might have as familiar substances and where they tend to fall on the pH range, to give you just a few little pegs to kind of hang this information on as we're talking about it in terms of then calculating pHs and pOHs. Let me flip back to my notes then. All right, like I said, P is a function, okay? So not only am I allowed to have pHs, I can have pOHs. And later on down the line, we'll also get pKa's and pKb's, and some other variations are possible. So pOH is the negative log of your hydroxide concentration. Now here's another fixed set of values. For a given solution, if you added the pH and the pOH for the same solution, you get 14. Okay, what this does for you is it allows you to kind of find 3 other values based upon one single piece of information. So let me go through these 2 equations, and I'm going to flip back to the whiteboard and kind of show you how the box works. So let's pick on orange juice for a moment. Orange juice is a little bit less acidic than lemon juice. It's around 3.5. What's my hydrogen ion concentration? Remember, we're using H plus as the shorthand way of writing H3O plus, which is actually more truthful, but it's a little bit more of a pain in the butt to write. So it's kind of traditional to shorthand it as H plus. So if I know that my pH is 3.5, first thing I need to do is swap where my negative sign is. You need to move the negative sign from the right-hand side over to the left-hand side. And then you are going to use your calculator to take an anti-log. Depending upon what brand of calculator you have, usually this is using the shift or inverse function on your calculator. So for instance, I could put shift log negative 3.5 equals, and it should give me the value that you see there of 3.16 times 10 to the negative 4th. What if I knew my pOH? Now this adds one more step. Since I know pH plus OH equals 14, if I know pOH is 10.4, I can subtract, and then that gives me a pH of 3.6, okay, close to the one above, not exact, but close. Do my anti-log thing, and I get 2.5 times 10 to the negative 4th. All right, back to the idea of the box. All right, let's see if I can make this not look like a total mess. All right, so pH you know your pH, based upon that particular equation of pH and pOH equals 14, if you know one, you can find the other. Okay, but knowing the pH or the pOH also allows you to figure out concentrations. So I can figure out what my H plus concentration is. But that also means, based upon the idea that H plus and OH minus multiplied together give you KW, means I can also find my OH minus concentration. So like I said, this is what I refer to as the box method. Because all four of these values for any given solution are all dependent upon each other, and those two equations, one of them being OH times H plus gives you KW, 1 times 10 to the negative 14th, and pH plus OH, POH gives you 14. If you know one corner, this allows you to find the other three values always. Okay, so they are all interrelated to each other. All right, back to the weak acid concept. So remember, we're talking about equilibrium. And the HA is your acid before part of it has fallen off. It falls apart into H plus and A minus. If you write your equilibrium expression, because remember the water molecule actually is there, but it's not displayed. So I have H plus and A minus on the top, and I have the unionized version on the bottom. All right. I have some information in the next problem. I have pH, and I also specified that it was monoprotic. It has a single hydrogen that falls off. Its pH is 3.15. And I started this equilibrium with a concentration of 0.2 molar. What's my Ka? All right, we need to make some assumptions and then tie them together here. I'm going to assume that my H plus and my A minus match. It's like saying if I have one pair of shoes, presumably I have one left one and one right one. So same idea kind of applies here. So first, take your pH and anti-log it and figure out what your hydrogen ion concentration is. 7.08 times 10 to the negative 4th. Now we can assume that my H plus and my A minus are identical. And then how do I find my HA? Well, I know what my initial concentration was before a little of it flowed to the right to give me ions. So I'm going to subtract 0.2 minus the 7.08 to the negative 4th. I have a slightly lower value then for my HA, 1.993. Oh, man. I hosed that. I just realized my decimal is in the wrong place. I put my decimal between. Okay, let me fix this. Hopefully you guys can see this. It's supposed to be 0.1993. Yeah, that just totally doesn't work. If I even did it right 3 lines down, I actually have it correct. I just suddenly realized there, it's like, wait a minute, that doesn't work. Anyway, so back to fixed math now. I've got 0.2 becoming 0.1993. All right, now take all your values and plug them back into your equilibrium expression. That will give you 2.5 times 10 to the negative sixth. All right. What if we come at the same idea from a slightly different point of view? What if you know the Ka and you know your initial concentration, but you don't know the equilibrium concentrations? This kind of backtracks to all of the concepts that we used in general equilibrium. All the same ideas apply in terms of how you do the math. So I've got the unionized version, which I just shorthanded as HA. And then I've got my two ionized parts, the H plus and the A minus part. And I started out with 0.03 molar as my initial. No H plus and no A minus to start with. So the change means I'm shifting to the right. I am decreasing the amount of my HA, which means I then will increase from nothing up to a small amount of my H plus and A minus. And your equilibrium line in the ice chart then becomes 0.03 minus X and X. So looking at my Ka, it has an exponent of 10 to the negative fifth. I am uncertain as to whether or not I could shortcut this. So I actually crunched all the way through the quadratic in order to make sure I didn't run into any problems here. So first I put it in, I've got H plus and A minus on the top, so my X and my X. I've got the 0.03 minus X on the bottom. The 8 times 10 to the negative fifth is my Ka value. So algebra, algebra, algebra. Then we get to the quadratic. Okay, there's your first version of the quadratic. And then crunch it a little bit more. Crunch it a little bit more, such that I'm getting divided by 2 at the end. And like most quadratics, I ended up with a negative as one of my options. So yeah, I can't use that one. 1.51 times 10 to the negative third. That's how much H plus I have. That's how much A minus I have. And then I must subtract 0.03 minus that value to get 0.0285. I have enough pieces now. I can actually also figure out what the pH of this solution is. Since my H plus gives me the data I need, I can do negative log of 1.51 times 10 to the negative third. This ascorbic acid, which is vitamin C, solution has a pH of 2.82. Another thing that you can do, and I'm actually slightly annoyed that this split it across the let's do this. Make it a little easier to see. All right. Sometimes we are interested in percent dissociation. How much of the acid you dumped into the beaker fell apart compared to its initial concentration? 2%, 3%, 10%? So a melt dissociated on the top, which is usually a molarity value also. Initial concentration on the bottom. And then because it's a percentage, we need to multiply times 100. And so after I moved my line there to make it a little easier to read, H plus at equilibrium over initial times 100. So some generalities can be tossed out for this, in that your percent ionization, or sometimes called percent dissociation, they both mean the same thing, is related to the strength of the acid. And weirdly, the more dilute your acid, the weaker your acid, the more it actually falls apart. And that sounds weird. That doesn't sound like it should work that way. It would seem that if you took a beaker that had some acid in it and you dumped a batch of water in it, it would seem that that should make the percent dissociation also go down, as well as the concentration, but it doesn't actually work that way. The way the equilibrium's set up tends to influence this is, if you have more water, it allows for more of the pieces of the undissociated to then separate and become dissociated. All right, I picked on formic acid. Formic acid is the kissing cousin of formaldehyde. Okay, we saw aldehydes back at the beginning of the semester, and formic acid is a carboxylic style acid. So I want to figure out what the percent dissociation is for 0.417 molar formic acid. I looked up my Ka value. There is a Ka table in your chapter. There is also a Ka table at the end of the textbook. And I think there is an abbreviated Ka table in the back of your lab book. I did not bring my lab book with me down to my office tonight. So I can't give you an absolute guarantee on that, but I think there's a Ka table in the back there. All right. All of these problems kind of start out looking very similar in that two pieces on the top, one of them positive, one of them negative. The unionized version, the molecule all still assembled, on the bottom. I didn't put my chain, I kind of short changed my my ice chart here. I didn't give you the C line, but at this point we've done enough of them that you should start to recognize the pattern. So my unionized acid had an initial of 0.417. Once I hit equilibrium, it's a little bit less, 0.417 minus X. When I first dumped my formic acid into the beaker, there weren't any H pluses and there weren't any formates. Therefore, my X value and my X value are identical to each other. All right, back to the setup for your quadratic. So I've got Ka value of 1.8 times 10 to the negative fourth. I've got X and X on the top. I've got 0.417 minus X on the bottom. All right, gotta crunch this all together so I can do my quadratic. Remember, quadratic has to be ax squared plus bx plus c as its format. This is a messy one. My A value is 1, but my B value is 1.8 times 10 to the negative fourth. And my C value is 7.5 times 10 to the negative fifth. Crunch it all through the quadratic. And I showed you all my steps here, so you can go back and have a look at this. Once I finish all of this, I have two roots, and kind of per normal, one of my roots is negative, so negative 8.7 to the negative third. Yeah, can't use that one. My positive one is 8.56 to the negative third. That's what goes on the top of your percent dissociation equation there. So 8.56 to the negative third on the top, 0.417 on the bottom. Remember, multiply by 100 because we want a percentage, not a decimal. And this was 2.5%. Okay, I will tell you this. I could have shortcutted this. It turns out, if you go back and you look at your values here of polarity of 0.417 and a Ka of 1.8 to the negative fourth, kind of eyeball that and go, well, if I wrote 0.417 in scientific notation, that would give me 4.17 times 10 to the negative 1. And my Ka is 10 to the negative fourth. If you have a 3 exponent difference or more, okay, or more, very definitely. But if you have a 3 exponent difference, you can often shortcut this. And I didn't actually go back and redo it by the shortcut method, but you could, and you would end up with really, really awfully close to the same value. I think instead of getting 8.56 to the negative third, I believe if you use the shortcut method, you get 8.55 times 10 to the negative third. Very, very minute difference, which is why they would allow you to use the shortcut method on this. If your value comes out as more than 5% and you had used the shortcut method, then you're kind of hosed. Okay, you're going to have to go back and redo it by the quadratic method, because rule of thumb says that if your percent dissociation is greater than 5%, you are not allowed to use the shortcut method. So sometimes it's a little bit of an educated guess. That's why I said, look at your exponent on your concentration. Look at your exponent on your Ka value. If there's more than 3 orders of magnitude, you can probably get away with a shortcut. If there's less, you probably can't. So keep an eye on that as we progress through this chapter, because that rule does continue to hold true. We kind of introduced that idea when we started the general equilibrium, but we continued that idea all the way through here into KAs. You're going to see it a little bit with KBs. We're going to eventually hit a variation on that when we get to KSPs. So all of that kind of ties together. There are some general rules that kind of linger all the way through equilibrium. Here's another one that goes backwards. Remember that your Ka, like most Ks, is for a particular temperature. But we just said percent ionization might change based upon dilution. So what if I actually know the percent dissociation? Can I go backward and find the Ka? Yep, that works. Set your percent, in this case, I had 6.1 as your answer, basically, and backtrack your way such that you have X on the top, you have initial concentration on the bottom, 0.02, and you have times 100. So I did a little algebraic rearrange here. You get 6.1 over 100 times 0.02. So your X value is 1.22 times 10 to the negative third. It's not quite the end of the answer though, because I need a little bit more pieces to the puzzle in order to make this all kind of hang together and then find my Ka value. Assumptions, okay. HA has to be original, which in this case was 0.02, minus your dissociated amount. So in this case, I've got 0.02 minus 1.22 times 10 to the negative third. That will give you a slightly smaller value of 0.01878. We can assume that your hydrogen ion concentration and your A- concentration are both the same, 1.22 times 10 to the negative third. And then you're just plugging it back into your Ka values of putting the two ionized parts on the top, putting the unionized part on the bottom, crunch all your data, and you should end up with a Ka value of 7.9 times 10 to the negative fifth for this particular set of data. I'm only going to barely touch on some base stuff tonight here, since you have an upcoming test, although we are going to kind of continue onward on Thursday. But I don't want to dump too much at one time. All right. Acids, bases, they kind of are a thing together. We have weak acids that have Kas. So it gives you a very similar feel here in that you have weak bases and Kbs. Okay, so Kbs go with your bases and Kas go with your acids. Although it's a little bit more complicated than that, we'll eventually get into another layer of this. We talked about bases a little bit at the beginning of the chapter. We said strong bases, kind of like strong acids, mean that they are probably about 100% ionized. So there are three that all the textbooks agree on. And then there's this other one. See, I said occasionally. Okay. Occasionally means some textbooks toss it in with the three normal strong bases, but you will also run across some that say that no, it doesn't quite get included. So we'll guarantee you that sodium hydroxide, potassium hydroxide, and barium hydroxide, which has two OHs in it, are all strong bases. The MgOH will dubiously toss that one in and say that it might be considered a strong base along with the other three. Think about this in terms of this allows you to figure out what your hydroxide concentration is. Okay. And the last example here that I want to do tonight has to do with using barium hydroxide. Now, this one's got a little extra layer of, we'll call it complication to it. Because barium hydroxide has two OHs in it, if I want to find the pH of a 0.23 molar, I have one more little piece to this puzzle. Okay. 1 mole of barium hydroxide would give me 2 moles of OH minus. Go all the way back to stoichiometry. Stoichiometry is a way of giving you your relationship with your coefficients. So 0.23 molar barium hydroxide gives you 0.46 molar, twice as much, hydroxide alone concentration. Take your POH, so negative log of 0.46, and use that equation, and I'll go ahead and kind of type this out here so you can see it, in that what you're doing here is you're saying that, actually, never mind. I just realized I missed a line and didn't look down. So POH is 0.34. Okay, here's the line that I was about to type because I didn't realize I had actually remembered to do that. So 14, that constant fixed value, minus POH will give you pH. Okay, and this makes sense. We're talking about a strong base. Think back about 3 pages. Okay, when we started talking about pHs, we said really powerful bases are up at the high end of the pH world. So finding out that this has a pH value that's getting close to 14 is actually not surprising because you have quite a high concentration of hydroxides in comparison to other substances we looked at. Okay, as we continue through this chapter, we are going to hark back to some of the things from the beginning of the chapter again of Bronsted-Lowry. Okay. In this whole, remember we had the idea of if you have protons, you can swap them around. And we had acids and bases and conjugate acids and conjugate bases. All that's going to kind of circle back again. This chapter has a lot of overlapping pieces to it that all kind of tie together because acids and bases are kind of a whole topic. You can't, acids by themselves is kind of an incomplete topic. You have to sort of do acids with bases because they fit together. All right, questions about the upcoming test or about acid stuff, acid-based stuff that we covered tonight? And James and Kelly, I sent you a little message through the chat function. Make sure you check that. I'm trying to catch up on some people who had some file misloads in terms of some submissions. And also a thing to remind, since I have the majority of you for lab also, is I have begun to put zeros into the gradebook system for labs. You can still turn stuff in and I will correct it when you turn it in, but a number of people owe me a number of things. So I'm trying to make sure that everybody is aware of what they've turned in and what they haven't turned in yet, because we are now basically halfway through the semester. So a number of people need to kind of get a little organized and get some stuff turned in. Questions? Otherwise, I will see some of you tomorrow night.